The Richter scale is a way of measuring the amount of energy released based on the volume of that snap. Now, first thing, make this absolutely clear, there is no such thing as the Richter scale. The Richter scale, okay, there is such a thing as the Richter scale, but it exists only in Southern California. I'll tell you why in a minute. The Richter scale uses waves that travel through solid rock to estimate the size of the amount of energy released from an earthquake and the size of an earthquake. If you have a recording, like an earphone to the ground, you can actually pick up seismic energy. You have P waves and you have S waves. P waves are sound waves, they're pressure waves. If we look at this, you can imagine molecules or individual minerals in the rock or rock bits expanding, contracting, expanding, contracting, expanding, contracting as they go down the line as the energy is propagated through the rock. Same thing happens in air with our voice. We have air molecules that bang and expand and contract between your vocal cords and your ear. Eventually that expansion and contraction hits your eardrum and you hear something. Those are P waves. They tend to be high velocity, so we also call them primary waves. P waves are primary waves. Shear waves or secondary waves are waves that go laterally to the direction of propagation. So remember when you were kids, I don't know if you ever did this when you were kids, it's something we used to do all the time because we were poor when I grew up. You take a rope or a jump rope or something and you'd move it in one direction like this, you'd see the wave that actually propagated down the length of the rope, but the displacement was perpendicular to it. That is what they call latitudinal S waves. The S waves are also called secondary waves because they tend to arrive after the primary waves, and the distance between the pressure wave and the secondary wave, the P wave and the S wave, can be used to estimate how far away the earthquake was if you have a rough idea of how fast these different waves travel through the rock. Surface waves are a different phenomenon. They're kind of an interference pattern between pressure waves, shear waves, and the surface. They tend to get complicated mathematically. We're not going to talk that much about them, but as you can tell from this image, they are much higher magnitude, and they're what's responsible for causing a lot of the damage in buildings. The question I want to talk about in class next time is, what is it that can cause these variations in body wave amplitude? So you can see here there's a certain amplitude of these waves. What could make those bigger or smaller? Come up with some ideas. Let's brainstorm on them in class. Okay, I mentioned there's no such thing as the Richter scale. When you hear somebody on the news say, oh yes, that earthquake that occurred in China was a Richter magnitude 6, that's a misnomer because, well, I can't tell you why because we'll have to discuss this in class. I can't give it away. The better way of measuring especially large magnitude earthquakes deals with how much material is actually moved. We're going to call that the moment magnitude. The moment magnitude is very much like work in physics. Now, we take you back to high school physics. I know, stick with me. But you remember, perhaps, that work is a force times a distance. If you take a cup and you move it from here up, you're doing work on that cup because it took a force to move that and you moved it over a certain distance. If I take it from down here and move it higher, I've done more work on that. Moment is essentially the same as work, except that it occurs on an arc. One complication, interesting fact, thing that makes plate tectonics really kind of cool, makes it a little bit more difficult, is that everything happens on the surface of an Earth. So we don't talk about lateral displacements and work, but instead we talk about rotations and moment. This is getting into the woods a little bit, but for the physics geeks in the classroom, moment is going to be related to displacement, but rather than how much length you're displacing, how long is the rotation arm at which you're rotating through. So in this case, the length of my arm is related to, and how much my fist would weigh is related to how much moment release there is, how much moment it takes to move my fist from point A to point B. It's a little bit different, and yes, it's a technicality, but stick with me, and you'll see why I think moment magnitude is a much more effective tool for measuring magnitude. Okay. One interesting thing to think about with all earthquakes and faults, we've got these faults that occur at plate boundaries and they break. That's where earthquakes occur. They're sliding past each other and eventually they can't slide anymore and they slip. Well, at some point they've got to stop and they've got to start. The whole fault, the whole length of the fault cannot rupture physically. So what actually people are starting to be able to map are surfaces of rupture, or actually rupture area. The stippled area in this diagram you can see in front of you represents the area of the fault that actually slipped. Now, at the very boundary, it's not going to slip at all, and in bits in the middle, it could slip a lot more. So it's going to be distributed throughout that whole area, but that is going to be more telling about how much energy is released during that earthquake. This is actual data from the earthquake that hit Japan, and you can see in blue, outlined in blue, is the entire fault plain. You can imagine the subduction zone would go down beneath Japan as the Pacific plate subducts beneath the Eurasian plate here. And the area in red represents the most slip that occurred during this earthquake. You can see in this graph, it's an extraordinary amount of slip. In some places, it approached 30, 40, or 50 meters worth of slip. That's an awful lot, and I'm not sure that number's right. I want to check that out again. Hope my battery doesn't die. That's an awful lot of slip, and I hope I want to check that out again. You can see the plate velocity is coming in at 8.3 centimeters per year. It's pretty fast, so it could have accumulated a lot of strain since the last earthquake. So to measure moment magnitude, we actually have to calculate the moment first. And this very simple equation tells us how to calculate the moment. A, in this case, represents the area of the fault plane. How big is that area in blue? Yeah, it's going to be complicated, but you can do some calculus to figure out what the actual area of slip is. It's not going to exactly be that, but it's going to be focused in different places and distributed over that whole rectangle. D is the amount of displacement. That's, again, the velocity times the amount of time since the last earthquake. Again, that's going to vary different places along that fault plane, but really smart people can figure that out. And this mu is actually a physical property of the rock. It's called the rigidity, or how strong the rock is, but we're not going to worry about that so much. To take this value of moment and turn it into a magnitude, it's something quite similar to what we know as the Richter scale. You put in this very simple equation. You just take a very large number. It's going to be 10 to the 22nd or something for the moment. Take the log, that'll give you something like 22, and you take 2/3 of that, and et cetera, and you get to something around 8 or 9. And that'll tell you exactly what the magnitude of this earthquake is. You notice this is a logarithmic scale, which means that for every increase in moment magnitude of 1, you're going up a factor of 10 in the amplitude, or the amount of energy, not energy released, but in the magnitude of the earthquake. I'll tell you why it's not energy in a little bit. Okay, so we now have a good grasp on what causes the size of the earthquake. Large earthquakes occur in places where you have very fast plate velocities, where you haven't had an earthquake in a long time, and where you can actually have a large area available for failure. Remember, from these low-angle thrust faults, where you have a lot of area that can be exposed before it gets to that brittle ductile. You have a lot of area exposed before it gets to that brittle ductile transition. You can create a very large area that can rupture, and that's why you get the biggest earthquakes there, versus the normal fault areas where you've got high heat flow close to the surface. Therefore, it's hard to actually have that much area to rupture, let alone worry about velocities and all that. What we want to get to in this class, however, is a discussion about where the largest earthquakes occur is very important, but also where must the riskiest earthquakes occur, the ones that pose the most damage to humans. That's going to be a factor certainly of the size of the earthquake, but I want to get into the other factors also about how this earthquake interacts with human populations. When you have a look at the Wisner reading, I want you to think about this one very simple pseudo equation. Now, this isn't you don't plug in numbers to this. This is just a conceptual equation to help us think about how does a geophysical hazard, something like an earthquake or a tsunami or a typhoon or a heat wave, interact with a vulnerable population. This is not quite so obvious, but if you imagine if you have an earthquake that happens in an area where there are no people, is there a risk posed? No, there isn't. So it's a very complicated thing, and that's what we'll be going into in the next part of class.